Greetings, geometry students. We're about to get into a deeper three-dimensional unit, looking at some more complicated surface area and volume formulas and calculations and shapes and stuff like that. And we are going to begin by looking at one of the figures that we kind of ignored as we moved through the solids unit, and that would be the spheres. Our objective for the day will be to acquire vocabulary for spheres and formulas for their surface area and volumes. Now, you may be familiar with some of these terms and possibly even some of these formulas, depending on how good your junior high teachers might have been over the years. So some of you may have a little bit of a head start on this, and some of you this may be mostly new for you. But as always in geometry, it's not that things get so much more difficult as the year goes on. It's just that the shapes get a little bit more complicated, and that does make the formulas get a little bit more complicated. But as you're going to see, the formulas still are just plug and chug. If we can find the right information to plug into the formulas, all we have to do is simplify the problem, and we have our answer. Okay, so let's take a look at some basic vocabulary here. So far, our calculations have been strictly towards figures that have had bases. Okay, so our calculations and discussions of surface area and volume have been limited to the figures that have two parallel congruent sides that we can call bases, in other words, the prisms, and other figures, other solids that only have one base and an opposing vertex across from that, the vertex, and those would be the pyramids. Today we're going to look at the only figure that we're going to cover in geometry that has no base, and that would be the sphere. Now, there are other spherical type objects in the world, obviously. The sphere is not the only one. Those other objects that are more like three-dimensional ellipses or things that are kind of peanut-shaped, stuff like that, those are called spheroids, meaning they are spherical by nature, but they're not perfectly round. Okay, but we're going to limit our focus to the spheres. Okay, so basic vocabulary here. Some of this you are familiar with, others maybe possibly not. Now, of course, circular objects, one of the biggest things that we need to know about a circular object is its radius. Now, that is still true when it comes to the sphere, but of course, a sphere radius cannot just measure any direction away from the center. Like a two-dimensional circle, it can also go in any of the three dimensions. So our radius right now is positioned over to the right, but it definitely could have gone to the left or come forward or gone backwards. And of course, with being a sphere, it could go upwards or downwards or any measure of diagonal that you can think of. And of course, the diameter still goes all the way across, twice as big as the radius. A term that might be new to you would be the concept of a great circle. Now, the great circle comes with a definition, and the great circle is the term that we use to describe the largest circumference that a sphere can produce. And typically, or not typically, but just kind of a real world demonstration, one of the things you can think about is the equator. The equator of our planet is what we would call the great circle of Earth. Okay, that's the largest circumference that our planet has to offer. Now, obviously, as you move north from the equator or south from the equator, technically those are also circumference if you travel around the planet going parallel to the equator. However, those aren't the largest circumference that the planet would have to offer. That would be the great circle. Okay, now the basics of the formulas, just like with two-dimensional circles, the only piece of information that we need the sphere to provide for us is the radius. Now we can get the radii or the measure of the radius in different ways. Of course, the problem could give it to us, or maybe it gives us a diameter, or maybe it even gives us information about the circumference. We could use information about the circumference to figure out how big the radius would be. Or maybe we could find the radius from the volume formula and then plug it into the surface area formula. At any rate, our formulas are the volume equals 4/3 times pi times the radius cubed. And of course, this is cubed. The radius is being cubed because volume is a three-dimensional measurement. Surface area's formula is 4 times pi times the radius squared. And the radius is squared because surface area is a second dimensional measurement. Let's take a look at a basic example here. Find the surface area and the volume of a ball that has a diameter of 10 inches. Well, once again, to find surface area or volume, all we need is a radius measurement. As we said, that radius measurement could come from anywhere. It could come from they give us the radius, or they give us diameter, or they give us surface area, or they give us volume. All of those measurements have the radius in them. We just have to get it out. Okay, so in this case, they gave us diameter. So the surface area formula is 4 times pi times the radius squared. All we need to know is the radius. Radius would be half of the diameter, so our radius is 5. Now, just like we've been doing here lately, we do not mind converting this pi into decimal form, but of course we could leave it in terms of pi if we needed to. At any rate, please remember to follow your order of operations. Please excuse my dear Aunt Sally. The exponent needs to be dealt with before the multiplication. So the first thing that needs to happen is 5 needs to be squared. That would be 25. You can multiply by 4. That would be 100. And 100 times pi, 3.14, would give you 314.16 inches squared. And it's okay to round off to the hundredths place once you get to the answer. Some of y'all need to quit rounding off in the middle of the problem. We only round off when we get to the answer. As for volume, volume comes with a formula as well. Volume is 4/3 times pi times the radius cubed. So once again, all we need to know is the radius, and we know already that the radius is 5. Okay, so once again, pay attention to the exponent first. 5 cubed means 5 times 5 times 5. That is 125. That 125 is in the numerator, so it's going to multiply with other numbers that are in the numerator. Okay, so that would be the 4. Okay, so 4 times 125, that's 500. Divided by 3 is about 166 2/3, and then times pi, 3.14, that's going to kick it up a little bit higher than 500 again. That's going to be 523.60 cubic inches. And of course, keep in mind, surface area is a second dimensional measurement. That's how come that you had inches squared for surface area. Volume is a third dimensional measurement. That's how come we have inches cubed for volume. Now, a lot of times, since the formulas are complicated, but the calculation is not that difficult, a lot of times what they're going to do is they're going to make it a two-step problem, meaning you're going to have to solve for the radius before you can use that radius to solve for something else that is missing. So let's see if you can't give that a try. Okay, here we have an example. If a sphere has a circumference of 25. So we'll assume that that is the great circle, and then we need to find the surface area of that sphere. Okay, so copy this down. I want you to give it a try. The circumference is 25 centimeters, and the circumference of a circle is 2 pi r. So you're going to have 25 equals 2 pi r. You can use your calculator and solve for your radius, and once you know your radius, you can plug it into the surface area formula, 4 times pi times the radius squared. Give it a try, bring that answer with you to class, as well as this next example. If a sphere has a surface area of 1,000 square feet, then what is its volume? Well, once again, we have a formula for surface area, 4 pi r squared, and we know that that surface area equals 1,000 square feet. If we can solve that formula for the radius, then we can use the length of that radius to plug in to the volume formula and then solve for our volume. Okay, so give that one a try as well. We will cover those examples when we get to class, and hopefully you will have at least gotten close on those values. At any rate, not too long of notes this time, just getting our feet wet, getting into this next unit. I appreciate you finding time to get your notes taken care of, and I will see you in class.